In our last section in Chapter 5, we're going to talk about how we can do a change of variables in double integrals. So what we're doing is analogous to when you learned how to do a u substitution it was probably in Calc 1. The idea that you can change all the x's to u's, and then you also have to change the dx to a du. And so the concept that we're going to be learning in this section is how to apply that to multivariate functions, so to functions of more than one variable. And we've actually already talked about a couple of specific changes of variables. The one I want to consider right now is changing from rectangular to polar coordinates. That is a change of variables, and we have seen how we can do that change of variables in an integral. We can replace the x's with r cosine theta, the y's with r sine theta, and then we learned that we have to replace the dy dx with an r dr d theta. And so our goal is to generalize the process and talk about how we can do other types of change of variables as well. So I'm going to start just to help us kind of think about this polar coordinate transformation in a slightly different context. I'm going to start by thinking about the region x squared plus y squared equals 4 in the r theta plane. So let's see if we can draw that region in the r theta plane. So I'm first going to draw what we're talking about in the xy plane. X squared plus y squared equals 4 is a circle with a radius of 2. And so that's what I've drawn. We can describe this set of points that I've shaded in polar coordinates as all points with r values from 0 to 2 and theta values from 0 to 2 pi. So we could actually take this description, r from 0 to 2, theta from 0 to 2 pi, and we could draw this in an r theta plane. So basically what I've done here is I've drawn an r-axis and a theta axis. And then I'm going to indicate that the r values always go from 0 to 2, and the theta values go from 0 to 2 pi. So in the xy plane, we had a circle, but when we do this transformation, we now have a rectangle in the r theta plane. And integrating over a rectangular region is much easier than integrating over that circular region. So let's try to do something similar for a more generic change of variables. Let's consider the following transformation. X equals u plus v, y equals 2u plus v. Let's see if we can sketch the region that I have drawn to the left, which is in the xy plane. Can we sketch this in the uv plane? So the very first thing I'm going to do is I am going to try to get these equations solved for u and v. So I want an equation for u and an equation for v. And so I can think of this as a system of equations that was given to me. And I'm going to use the method of elimination to try to solve this system for u and then for v. So again, same system, I just copied it down on the screen a little bit lower. If I want to solve for u, I need to make the v's disappear. So using that process of elimination, I'm going to take my first equation, I'm going to multiply it by -1. That gives me minus x equals minus u minus v. And then the idea is if I add that to my second equation, the v's disappear. It's using that process of elimination. On the left-hand side, we've got minus x plus y, that's y minus x. And then on the right-hand side, minus u plus 2u is just u. And so there's my equation, u equals y minus x. So the u values will always be the y values minus the x values. And then I'll do something similar to solve for v. So same two equations, same system of equations. If I want to solve for v, I have to get rid of the u's. And so I'm going to take this first equation and I'll multiply everything by -2. because then when I add them together, the u's will cancel out. So negative 2x equals negative 2u minus 2v. I add those together. So I add that equation with my second equation. Let's see, minus 2x plus y equals, the u's cancel out, minus 2v plus v is negative v. And then I'll just go ahead and divide everything by negative 1. So v is 2x minus y. So I just took the equations given, solved them for u and v, because now I can transform all the points in my image into u and v coordinates. So what I mean by that, if we consider the point 0, 0, so x is 0, y is 0, we can plug that into our u and our v equations. If x and y is 0, u is y minus x, so 0 minus 0, and v would be 2 times 0 minus 0, that's also 0. So the point at the origin, when we transform that into the uv plane, well, it's still the point 0, 0. All right, what about the point 2, 2? X is 2, y is 2. So then u would be, oops, go back. U would be y minus x, so 2 minus 2 is 0. And v would be 2 times 2 minus 2, that's 2. So that becomes the point 0, 2. And then I'm going to go through and do the same thing with the other points given. So x is 3, y is 4. 4 minus 3 is 1, so u is 1. 2 times 3 is 6, minus 4 is 2. And then finally the point 1, 2, I plug x equal 1, y equal 2 into my uv equations. U is 1, v is 0. Finally, they want us to sketch this region in the uv plane, so I'm just going to go ahead and draw these points and connect them in the same order they are on the screen. Okay, so the point 0, 0, we just learned stays at 0, 0, and it is connected to the point 2, 2, which moved to 0, 2. The point 2, 2 is connected to the point 3, 4. So let's see, that means in the UV plane, my point 0, 2 is connected to the point 1, 2. And then finally, the last point we have to put on there is the point 1, 2. In the UV plane, that's 1, 0. And so this, I guess it's a parallelogram in the XY plane. We transformed it to the UV plane, and it's now a rectangle. So that's kind of the idea or the concept here, the process that we're doing, is when we have certain regions, we can transform them into simpler regions to work with. So I want to switch gears really quickly because the whole reason we're talking about these transformations or change of variables is with the goal of solving integration problems, setting up multiple integrals. And so before we can do that, I need to define something called the Jacobian. And so I've got two different ways to denote the Jacobian. I can use the capital letter J. So J of UV is my Jacobian for the transformation to UV. Or you might see dxy over duv. That's just another way of writing the exact same thing. I'm going to define my Jacobian using this kind of determinant notation that we've done in the past when we talked about, for example, cross products. So I'm going to create a matrix. I'm going to put my derivative of x with respect to u, derivative of x with respect to v in the top row, and then the bottom row, derivative of y with respect to u, derivative of y with respect to v. And then to actually evaluate this, I'm going to take dx du, let's go back, times dy dv, and I'm going to subtract dy du times dx dv. When we set up our multiple integrals with the change of variables, we're going to be able to replace the dx dy with the absolute value of our Jacobian times du dv. I'm not going to have time to derive that for you, but let's just do some examples, see what I mean by that and how that works. So rather than deriving that, let's actually do an example with a Jacobian where we know what the result should be. For example, let's consider finding the Jacobian for our transformation to polar coordinates. So before I even start this problem, I do want to point out that we have already learned that when you're writing an integral in polar coordinates, you can replace the dy dx with r, dr, d theta. So let's see what happens when we compute our Jacobian. So I just jotted down my definition. So my Jacobian for the transformation to r and theta, I'm going to take dx dr, dx d theta in my top row of my matrix, dy dr, dy d theta in the bottom row of my matrix. So that means I have to find my derivatives of y and x with respect to both r and theta. Derivative of y with respect to r is just sine theta. Derivative of y with respect to theta would be r cosine theta. And then dx dr is cosine theta. Dx d theta would be negative r sine theta. So I'm just going to go ahead and put those into that matrix and then multiply. Let's see, we're going to get r cosine squared theta minus negative r sine squared theta. Let's see, that's r cosine squared plus r sine squared. We can factor out an r. We're left with r times cosine squared plus sine squared. Cosine squared plus sine squared is just 1. And so that simplifies all the way down to r. So the Jacobian for the transformation to polar coordinates is just r. And so what that means is when we do this transformation, we can replace the dx dy with the Jacobian, which is r, times dr d theta. And that's exactly what we have learned in the past. This is just a different way of thinking about where that r comes from. And the advantage of these Jacobians is we can generalize this and apply this to other transformations. So for example, if I want to find the Jacobian for the transformation x equals u plus v, y equals 2u plus v, I can use the exact same process. I'm going to find my derivatives. So derivative of x with respect to u is 1. X sub v is 1. Derivative of y with respect to u is 2. Derivative of y with respect to v is 1. And then I'm going to go ahead and put those derivatives into my kind of determinant form. And so to compute my Jacobian, I'm going to take 1 times 1, which is 1, minus 2 times 1, which is 2, and I get negative 1. So my Jacobian is negative 1. So finally, let's put all of this information together. So same kind of transformation. We're going to consider this transformation x equals u plus v, y equals 2u plus v. So I've just copied that down over here. Same transformation, x equals u plus v, y equals 2u plus v. And let's see if we can evaluate the integral x times y over the region I have drawn in the left. So to save some time, this is the exact same region and the exact same transformation we worked with earlier. So earlier, if you go back to earlier in this video, when we solved this transformation for u and v, this is what we got. This was one of my first examples. So if x is u plus v, y is 2u plus v, then u would be y minus x, and v would equal 2x minus y. We sketch this region in the uv plane by taking these corner points and transforming them into u's and v's. And I've recreated that sketch that I did earlier. In the uv plane, we now have this rectangle where the u's go from 0 to 1 and the v's go from 0 to 2. So again, this is the same region, same transformation we talked about earlier. So let's actually see if we can apply everything we've learned to evaluate an integral. So how do we put all this together? I guess the other thing I should remind you of this, we just computed the Jacobian for this transformation and we got -1. So putting all of this together then, we can rewrite this integral by replacing the x with u plus v, and then replacing the y with 2u plus v. So we're going to integrate u plus v times 2u plus v, and then we're going to change this dA into the absolute value of our Jacobian times du dv. Absolute value of -1 is 1, and so I'm just going to stop writing that 1 down. Now I can put in some bounds of integration. Looking at my transformed region, the u values go from 0 to 1, and the v's go from 0 to 2. So this is the integral that I need to compute that is equivalent to the problem given to me. So to help me with the integration, I'm going to go ahead and I'm going to FOIL out the u plus v times 2u plus v. I ended up getting 2u squared plus 3uv plus v squared. And then I'm going to do that inside integral first. So I'm going to integrate with respect to u. I get 2u to the third over 3 plus 3u squared v over 2 plus v squared times u. And then I'm going to plug in my bounds of integration, the 1 and the 0, and again, I'm plugging those in for u. So I'm left with a 2/3 plus 3v over 2 plus v squared, and then I guess technically it's -0. My outside integral, so here's my result from the inside integral. Same thing, I just moved it higher on the screen so I had more room. So I'm now going to integrate my result, this 2/3 plus 3v plus v squared. I'm going to integrate that with respect to v. I get 2/3 v plus 3v squared over 4 plus v to the third over 3. And then I'm going to plug in the bounds of integration. So I'm going to plug in the 2, plug in the 0, subtract them. And assuming I didn't make any arithmetic errors, I got 7. This should add up to 7. Is that right? 4/3 plus, I guess 3 plus 8/3. Yeah, that adds up to 7. And there's my final answer. So through this explanation, I've done this one problem kind of in pieces. And so the next thing I'd like to do is kind of run through a couple examples where we work through this long process in its entirety. And so what we're going to do in these problems is we are going to sketch the region given in the xy plane. And then it's frequently helpful to have equations of the curves that form the boundary. And that's because for step 2, depending on the region of the integrand, we are going to choose our transformation. And it's frequently useful to choose a transformation that matches the curves that form the boundary. And the idea is then we can take our region and make it simpler, ideally a rectangle. Sometimes we're going to choose our transformation based on what we're integrating, and I'll explain that when I actually do examples. So we're going to sketch our region, and then we're going to pick a transformation that matches either the region or the integrand, hopefully both. We can then find our limits of integration in the UV plane, and so I usually then redraw that region in the UV plane to do that. We're going to compute our Jacobian, and then we're going to rewrite our integral in terms of u and v. So we're going to replace the variables in the integrand, and we're going to replace our dA with, I should have put absolute value. It's absolute value of the Jacobian times du dv. All right, so let's put all of this together and try to solve the following problem. We want to integrate x plus y squared times sine squared of x minus y over a region that is a square with vertices at the following locations. So I'm going to go ahead and sketch that square. And so I just plotted the 4 points given. So this is in the xy plane. So I plotted the point pi 0, and then 3 pi over 2, pi over 2, pi, pi, and pi over 2, pi over 2. And I kind of have this slanted square here. So that's the region over which we're integrating. Now, based on the thing that we're integrating, based on the function that we're integrating, it would be convenient if my u is x plus y, because that's inside my integral, and perhaps my v is x minus y. So that's a nice thought of what would be a good choice for the u and the v. I also noticed that if I look at the region that was given to me, the lines that form the boundary, this line down here, let me kind of highlight it. So this line I'm going to do in, I don't know, blue. If we write the equation of that line, that is the line x minus y equals pi. And this line right here is the line y equals x, or x minus y equals 0. So having either our u or our v equal x minus y is a good choice, because then the v's are going to go from 0 to pi. So using x minus y as a transformation is a really good choice. The other lines on my boundary are this one down here on the bottom is x plus y equals pi, and the one on the top is x plus y equals 2 pi. So that's another reason why using u equal x plus y is a really good choice for the transformation. So you want to pick your transformation so it matches the boundary and or the integrand, the thing you're integrating. In this case, the x plus y and the x minus y are things I see in both the region and within the integral. So I'm going to go ahead and take this transformation and solve it for x and y. And so I use the method of substitution to do this again. If I want to solve for x, I want the y's to disappear, and so I can just add these two equations together. So u plus v would equal 2x, the y's disappear. U plus v equals 2x. Divide by 2, so x would be 1/2 u plus v. If I want to solve for y, I can go ahead and I'll take the v equation, multiply it by -1, and then add them together. So u minus v, x's go away, equals 2y. Divide by 2, so y is 1/2 u minus v. Why did I solve for x and y? I did this because I need to compute that Jacobian. All right, before I compute my Jacobian though, let's draw our transform region in the UV plane. So I'm going to take my 4 corner points in the XY plane and I'm going to transform them into the UV plane using my transformation right here. So if x is pi and y is 0, X plus y is pi, and x minus y is also pi. So that point becomes the point pi pi. If x is 3 pi over 2 and y is pi over 2, u would be 3 pi over 2 plus pi over 2. That's 2 pi. And v would be x minus y, which is 1 pi. And then the other 2 points, pi pi becomes the point 2 pi 0. Pi over 2 becomes the point pi 0. And so then I'm going to go ahead and plot those points in the UV plane. So we've got the point pi pi, 2 pi pi, 2 pi 0, and pi 0. And so we still have this square-shaped region. It's no longer tilted. That's going to make it a little bit easier to set up our bounds of integration. All right, so next thing we have to do before we can actually write that integral is we have to compute our Jacobian. So I'm going to take the derivative of my transformations. So I'm going to take derivative of x with respect to u. That's 1/2. Derivative of x with respect to v is also 1/2. And then I'll find my derivatives of the y. Derivative of y with respect to u is 1/2. V is negative 1/2. And then I'm going to set up that Jacobian. So I put my derivatives of x on the top, y on the bottom. And then I'm going to go through 1/2 times negative 1/2 is negative 1/4. Minus 1/2 times 1/2. So minus 1/4 is minus 1/2. All right, finally, after all this introduction work, I'm going to go ahead and write my integral. So I can replace the variables with u's and v's, and then I'm going to replace my xy with my absolute value of my Jacobian, du dv. Okay, so what did we do here again? So this x plus y, here it is. There's my transformation. X plus y we can replace with a u, so u squared. X minus y we can replace with a v, so my function becomes u squared sine squared v. And then I'm going to change my dA into absolute value of my Jacobian times du dv. Or I can write this integral as 1/2 u squared sine squared v du dv. And then based on my picture, I can see that the u's go from pi to 2 pi. Those are my bounds of integration for u. And the v's go from 0 to pi. So those would be my bounds of integration for the v's. Whew, finally, after all of that, we are ready to compute this integral. So I'll do my inside integral first. I'm going to integrate 1/2 u squared sine squared with respect to u. I got 1/2 u to the third over 3 sine squared v. Plug in the bounds of integration. So I had to plug in 2 pi for u, plug in pi for u. Did some arithmetic, combined like terms. I got this to simplify down to 7/6 pi to the third sine squared v. So now I have to integrate 7/6 pi to the third sine squared v with respect to v. I'm going to use that power reducing identity to deal with the sine squared. I can replace sine squared with 1 minus cosine 2v over 2. Pull my constant out front. And I'm going to rewrite that power reducing identity as 2 terms, 1/2, and then minus 1/2 cosine 2v. Antiderivative would be 1/2 v minus 1/2 times 1/2, so 1/4 sine of 2v. And then I'm going to plug in my bounds of integration. which are pi and 0, and subtract them. Not forgetting about that constant that was in front of the integral. So I've got 7 pi to the third over 6 times 1/2 pi minus 0. So that becomes 7 over 12 pi to the fourth. And there's my final answer. Let's do one more. Same process, different problem. I want to try to integrate x minus y over x plus y to the fourth over the triangular region bounded by the line x plus y equals 1, y equals 0, and x equals 0. And so I have sketched the line x plus y equals 1 and shaded in the region that we're talking about. So the first thing I have to do is pick my transformation. Because I have a boundary that is an x plus y, using that as either my u or my v makes sense. And so I'm going to choose v equals x plus y. And then for the other transformation, if I just look at the problem, the function we're integrating has an x plus y, but it also has an x minus y. And so I'm going to go ahead and let u equal x minus y and v equal x plus y. So there's my transformation. I'm going to solve these for x and y. And I didn't show my work because this is the same as what we did in the previous problem. Maybe I'll go back. There it is. We had u equals x plus y, v equals x minus y. We solved them for x and y. So same kind of process, so I'm not going to show my work again. So if we solve these for x and y, we get x equals 1/2 u plus v, and y equals 1/2 v minus u. So I'm going to redraw the region in the UV plane. And so how did I do this? Same process as before. I just transformed all of these points. So if we have the point 0, 0, x is 0, y is 0, if we plug that into our UV, we get 0, 0. So that point didn't change. And then we've got the point 0, 1. X is 0, y is 1. So 0, 1, we get u equals -1 and v equals 1. So it's this point right here. And those are connected. So this line in blue is the same as the line in blue at the bottom. And then one more point, we've got the point 1, 0, x is 1, y is 0. So that's going to become, let's see, u is going to be 1, and v is going to be 1. That's right here. And then I'll just connect the other dots. So we still have a triangular region. It's just oriented in a different direction. All right, so there's our transformed region in the UV plane. And then I'm going to go through and I'm going to compute my Jacobian. So similar work to before. I'm going to find my derivatives with respect to x, derivatives with respect to y, plug them into that matrix. I'm going to multiply 1/2 times 1/2 minus -1/2 times 1/2. I get 1/4 plus 1/4, or 1/2. So my Jacobian equals 1/2. And now finally, I'm going to rewrite my integral. I am integrating. Oh, this should say 1/2. Let's fix that. There we go. I am going to be integrating u over v to the fourth, because u is x minus y, v is x plus y, so u over v to the fourth times the absolute value of my Jacobian, which is just 1/2 du dv. And then for my bounds of integration, I think I fixed this to 1/2 eventually. Just have to write it in for now. Okay, so bounds of integration, we'll do the u's first. The u values go from this line on the left, which is u equals -v, to the line on the right, which is u equals +v. So my u values go from -v to v. And then my v values, there we go, I finally fixed it to 1/2. My v values go from 0 up to 1. 0 to 1. All right, so the integral we're trying to compute is 1/2 u to the 4th over v to the 4th du dv. The v's go from -v to v, and the u's go from 0 to 1. There we go. Same problem, I just rewrote it at the top of the screen where I have more room. And so now I'm going to go through and actually compute this integral. We'll do our inside integral. So integrate with respect to u first. I get 1 over 2v to the 4th times u to the 5th over 5. I'm going to plug in my bounds of integration. So plug in my v to the 5th and my -v to the 5th. -v to the 5th is going to turn this minus into a plus. And then let's see, we can simplify further. I'm left with 1/10 v plus 1/10 v, 2/10 v, or 1/5 v. So that first integral becomes a 1/5 v. And then to finish, we're going to integrate 1/5 v with respect to v. I get 1/5 v squared over 2, or v squared over 10. Plug in my bounds of integration, and there's my final answer, equals 1/10. And so that is it. That's my final answer for this problem. That was my last example as well. So I think that was my last example. Yes, it was. So please let me know if anything is unclear in this video, and I would be happy to clear it up.